Let's explore how telescopes work by taking an example. Here I'm looking at the beautiful moon. Now you know what will make it even more beautiful? If I could zoom in and magnify this. And the first thing that comes to my mind when it comes to magnifying something is a magnifying glass. So let's go ahead and bring in a magnifying glass. Here it is. It's just a convex lens. Difficult to show that because it's pretty dark around. But I hope you can see. That's just a, yeah, there it is. You can see that that's a magnifying glass, a convex lens. Let's keep it close to our eyes and see what happens. We get just a blurred image. We don't see anything, just blurred moon. Why is that happening? We have seen in a previous video how a magnifying glass works in great detail. But in short, in order for the magnifying glass to work, the objects have to be within its focal length. If there's any object which is outside the focal length of your convex lens, it's just gonna look blurred. And we've talked a lot about this in a previous video, so if you need more clarity on this or if you need more details about that, it'll be a great idea to go back, watch those videos, and then come back over here. The focal length of the glass that I'm using is maybe 20-25 centimeters, and the moon is what? Thousands of kilometers away. So there's no way we can magnify the moon this way. You'll just see blurred images. So in order to use our magnifying glass, somehow we need to bring that moon closer to us. And that's what a telescope does. It brings a faraway object closer to you and then uses a magnifying glass to magnify the image. That's how a telescope, that's the principle of a telescope. So all we need to figure out now is how to bring that moon closer to us. This can be done just by using a convex lens. Let's look at the theory first. So here's our convex lens. Let's say it has a focal length of f. These are the principal foci. And far away, here is our moon, the object of our interest. So here is our giant moon. And we've kept our moon right on top of the principal axis. All right? Now to figure out what's going to happen, we have to draw some rays of light. And we'll do pretty much the same thing what we used to always do. We're going to draw rays of light from the top of the moon. One ray of light we will shoot from here all the way to the optic center of our convex lens. Now remember, we have to at least draw 2 rays of light from a given point, and usually we would draw another ray of light parallel to the principal axis, isn't it? But this time if we draw that ray is going to miss our lens because our moon is so huge. So we cannot draw another ray of light parallel to the principal axis. So let us draw another ray which is a little bit below. It's going to hit our lens a little bit below the optic center. So these rays of light, after traveling through vast distances, will finally come over here and hit our convex lens. So notice that the 2 rays of light, by the time they come over here, are pretty much parallel to each other. That's because they are originating from a point which is extremely far away, sort of like infinity. And we've seen the rays of light coming from infinity are almost parallel to each other. The ray of light that's hitting our optic center goes undeviated. We've seen that as well. And the blue ray, let's assume that blue ray passes through the principal focus of our convex lens. Well, we know that the ray of light that's passing through the principal focus, what happens to it? Well, it's going to go parallel to the principal axis after refraction. So the top part of the moon gets focused at this point over here. The bottom part of the moon is on the principal axis. So it'll get focused over here. And as a result, and so an inverted image of our moon is formed right on the principal focus over here. And we've seen this before, right? Rays of light which are parallel gets focused right on the principal focus. And now we can treat this image as our new object and we can magnify it using our magnifying glass because this is close to us. So notice how this convex lens has brought the moon closer to us. So this lens is usually called as the objective lens. So the purpose of the objective lens, so this is called as the objective lens. And the purpose of the objective lens is to bring, in some sense, bring the object closer to us, the faraway object closer to us. And so we'll call this as the principal focus of the objective, and we'll call this as the focal length of the objective. And since now this object is very close to us, we can go ahead, bring in our magnifying glass, and we can magnify it. So let's bring in our magnifying glass. So here's our magnifying glass. We usually call this as the eyepiece because it's kept very close to our eyes. And let's say its focal length is FE. We're writing that so that we can distinguish between these two focal lengths. And so now we can magnify this object. Now remember, to magnify any particular object using our magnifying glass. All we have to do is make sure that this object is within our focal length. That's the whole point. So we have to bring our magnifying glass and our eye closer. Not enough, not enough. We can bring it all the way till here, such that this new object lies right on the principal focus of our magnifying glass. And now, after refraction, the rays of light become parallel to each other because the object is kept right at the principal focus. And these parallel rays are now incident on our eyes, and our eyes can easily focus them on the retina. And look at the angle subtended by this new object. So we'll just have to draw a reference line from the top of this new object all the way to our optic center. We are assuming that the optic center of both the lenses are pretty much the same. So we're going to assume this is the optic center. And if we draw that, notice this is now the new angle that is formed right at our eye. And as a result, a huge image will be produced in our eye. And that's how this moon now will look very, very big to us. We'll talk more about this ray diagram, its magnification, a little bit later, but first let's demo this. So here's our moon one more time. So the first thing we'll do is bring in a convex lens, which is going to be our objective. Notice that's forming a real image close to us. So again, we're going to bring in a convex lens. That's our convex lens. Difficult to see that in the dark, but that is a real image formed very close to us. Now, of course, it's extremely difficult to convince ourselves that it's a real image formed very close to us because it pretty much looks the same. First of all, notice it's a little bit inverted. I don't know whether you can see that because the moon is round. It's inverted image. It's close to us. The only way to convince ourselves that this is close is now we can use our magnifying glass and bring that object within the focal length and magnify it. So let's go ahead and see that. So we have the image of the objective. We'll bring in now the magnifying glass. I'm preparing the magnifying glass. Just one sec. There it is. You're bringing the magnifying glass. We're going closer, just like what we did before. We're going closer to it. We're going closer. And now there it, this is difficult. Okay. But there it is. You can see the moon. Okay. I'm going to stop over here. We can see the moon magnified. So I took a couple of pictures. So here it is without the telescope, and here with the telescope. You can clearly see there is, this is a little bit more magnified compared to what we could before. Now, obviously the image is blurred because of many reasons. First of all, the lenses that I'm using are not ideal. They're bad lenses. There's a lot of distortions in them, and that's why it's not very clear. And more importantly, I'm holding the objective lens and the eyepiece and the camera with my hand, so it's extremely difficult to, position them. But hopefully, this demo could at least show you in principle how a telescope works.